Good evening once again, and you're welcome to the PJ's Physics classroom. We meet again today for the continuation of the gravitation. So before I begin, just a small recap of what we did in the previous episode of gravitation. Remember, we spoke about the Newton's law of universal gravitation, and we said that it relates the product of two masses arranged close to each other with the distance between them to get the force of attraction that exists between the two masses. We looked at gravitational field intensity, which we said that it is the force, the gravitational force per unit mass on a charge. And we looked at gravitational potential energy, the work done in moving a mass from infinity to a point in the gravitational field. Then we looked at gravitational potential, which is the work done per unit mass in moving that mass from infinity to a point in the gravitational field. So today we want to continue from where we left off. So we begin with this gravitational potential difference. And when we say gravitational potential difference, previously we looked at, in the previous episode, we looked at gravitational potential as the work done per unit mass in moving that mass from infinity to a point in the gravitational field. So now let us consider a mass which is already inside the gravitational field of another mass. Now we want to move this mass from one point within the field, within the same field, to another point within the field. Because the gravitational potential is inversely proportional to distance, based on the proximity, the distance from where the source of the gravitational force is to where the mass is. As the distance change, the gravitational potential also change. So the work done per unit mass in moving this particular mass from a point of low potential to a point of high potential within the same gravitational field is what we refer to as gravitational potential difference. So let me illustrate this on the board so that you can get the mathematical relation for it. For instance, so let us consider a gravitational field created by this mass, capital M. Another mass, M, is inside this field already, so that there's a gravitational potential field between them. Last week, we saw that this gravitational potential field is given by negative J M over R, where R is the distance between them. So let V1 be the gravitational potential between the two masses. Now we want to move this mass from this point P to another point Q. So the work done per unit mass, in moving this mass from a point of low potential to a point of high potential in a gravitational field is what we refer to as gravitational potential difference. We call it gravitational potential difference. And so the gravitational potential difference, delta V, is equal to V1 minus V2, where V1 is greater than V2. We subtract the point of low potential from the point of high potential. So that is gravitational potential difference. Let's look at another term we call equipotential surface. Within a gravitational field, there are some points within the field that are equal potential. These points form a surface within the gravitational field. This surface is what we refer to as equipotential surface. So we define equipotential surface as points in the gravitational fields that have equal potential. That is what we mean by equipotential surface. So we look at another term we call satellite. Now, we say a satellite is any heavenly body that revolves around a planet. You know, some people try and define satellites as a heavenly body that is a smaller body that revolves around a larger body. That definition is faulty. The reason is that an object qualifies to be a satellite if it revolves around a planet. So if you have a small bird that is revolving around a certain big building somewhere, then the bird, does that mean that the bird becomes a satellite? No. So a satellite is an object that revolves around a planet. A typical example of that is the moon. So we have two types of satellites: natural satellites and artificial satellites. A natural satellite is a satellite that is not man-made, that revolves around a planet. Example is the moon. An artificial satellite is a satellite that is made by man to revolve around the earth. Now we have two types of artificial satellites. We have passive satellite and active satellite. Passive satellite and active satellite. A passive satellite is a satellite that only receives signal in space and transmits the signal onto some part of the Earth's surface without any modulation, without any amplification. So if a satellite will receive the signal in space and transmit the signal without changing the frequency or the information the satellite has picked in space, that satellite becomes a passive satellite. However, if a satellite receives signal in space and the satellite modulates, the satellite amplifies the signal before transmitting it onto the Earth's surface, that satellite becomes an active satellite. But we also have some other artificial satellites that may either fall under passive or active. So we have a geostationary satellite. Now, when we say a satellite is geostationary, then literally we mean that the satellite is looking at only one spot on the planet. All right. Let's suppose that we want to focus on an object on the Earth's surface. Let this be the satellite. Let this be the Earth. So the satellite is positioned in space such that the satellite look at only one spot on the Earth's surface. It's able to take pictures of only one spot on the Earth's surface. But you see, the Earth is not stationary. The Earth is undergoing rotational motion. So if the Earth is rotating, the satellite cannot be stationary. The satellite must also revolve as the Earth rotates. The satellite must also revolve, something like this, you understand, so that the satellite can point at a particular spot. Such a satellite is called geostationary satellite. So we define geostationary satellite as a satellite that has the same direction and period of revolution as the direction and period of rotation of a planet. A satellite that has the same direction and period of revolution as the period and direction of rotation of the Earth, or you can say of the planet. Good. Such a satellite is called a geostationary satellite. Now there are three conditions for a satellite to be geostationary. One, the satellite must have the same direction as the direction of rotation of the Earth. So if the Earth is rotating this way, the satellite must also revolve that way. Two, the period of the satellite must be equal to the period of rotation of the Earth. Three, the satellite must be positioned around the equator. These are the three conditions for a satellite to be geostationary. An orbit of a satellite that has the same period and direction of revolution as the period and direction of rotation of the Earth, we call such an orbit a parking orbit. So geostationary satellites are launched into space to stay on a parking orbit. Alright? The orbit of a geostationary satellite is called a parking orbit. But don't use that as a definition. When they ask you to define parking orbit, you say it is the orbit of a satellite that has the same period and direction of revolution as the period and direction of rotation of the Earth. Good. Then we go to another type of artificial satellite that we call polar satellite. Listen to the name, polar satellite. So a polar satellite is a satellite that revolves around the Earth along the north and south poles of the Earth. Last question. Let's take this to be the Earth. You know the Earth is geospherical. Alright? So this is the north pole of the Earth and this is the south pole of the Earth. If I have a satellite that revolves around the Earth like this, alright, along the north and south poles, then that satellite becomes a geostationary satellite. Sorry, that satellite becomes a polar satellite. However, a satellite that revolves around the Earth like this, along the equator, we call that satellite geostationary satellite. So a geostationary satellite and then a polar satellite. Good. So these are some of the types of artificial satellites that you are supposed to know. Good. So before a satellite can be launched into space, alright, that satellite is given an initial velocity that we call escape velocity. We call that velocity escape velocity. So what is escape velocity? It is the initial velocity required for a satellite to just escape the Earth's gravitational field so that it does not come back. Let me explain this. If an object is within the Earth's gravitational field, then the Earth's gravitational force will pull it onto the surface of the Earth. We want this satellite to go up into space so that it goes beyond the Earth's gravitational field. When it is beyond the Earth's gravitational field, the influence of the Earth's gravitational force is not on the satellite, so the satellite will not be able to come back. The minimum initial velocity needed to cause the satellite to do this is what we call escape velocity. So we define it as the minimum amount of velocity needed for a satellite to just escape the Earth's gravitational field without coming back. That is what we refer to as escape velocity. So we try and obtain a relation for the escape velocity of a satellite. To be able to obtain a relation for the escape velocity, we must know something we call the conditions for a satellite to escape. Conditions for a satellite to escape the Earth's gravitational field. We have two conditions. Sorry, only one condition. We have one condition, which is the potential energy, the kinetic energy given to the satellite must be equal to the gravitational potential energy at the point of launch of the satellite. This is the condition for a satellite to be geostationary. So to obtain the escape velocity, we use this condition. Good. So we look at escape velocity. For purposes of this topic, let the escape velocity be VE. From the condition for a body to escape, we saw that the kinetic energy given to the satellite must be equal to the gravitational potential energy. So all of us know that kinetic energy is given by half mv squared, where v is VE, that is the escape velocity. That should be equal to the gravitational potential energy, G, capital M being the mass of the Earth, small m being the mass of the body that is supposed to be launched, the mass of the satellite, of course, and then R, where R is the distance from where we are launching the satellite till it escapes the Earth's gravitational field. Good. So for instance, if this is the Earth's surface and the Earth's gravitational field is like this, then the distance from here to here becomes R. Remember, because gravitational force is measured from the center of the Earth, the distance R is measured from the center of the Earth. Good. So when we simplify this equation, we get this. Okay, so half V squared, VE squared is equal to G, capital M over R. So we make V the subject. So VE is the escape velocity is given by 2gm over r all squared. This all square root. This is the formula for finding the escape velocity. What it means is that the escape velocity of a satellite is independent on the mass of the satellite. It only depends on the mass of the Earth, the universal gravitational constant at the distance, r. So let's do this. We already know that gravitational acceleration due to gravity J is given by J capital M over R squared. Alright? So let me manipulate this equation by multiplying 2 by R. I will get Rj is equal to J capital M over R. So look at this, J capital M over R. J capital M over R. So in place of J capital M over R, I can place Rj there. If I place Rj in this formula, then this formula will transform to become VE is equal to square root of 2jr. Square root of 2jr, where j is the acceleration due to gravity and r is the distance. Good. So we can use this formula or we can use this formula. Remember that acceleration due to gravity is also where we saw in the previous episode that the acceleration due to gravity J is also equal to the gravitational field intensity at that point. The acceleration due to gravity at a point is equal to the gravitational field intensity at that point. So because we are launching the object from the surface of the Earth, we can put the gravitational field intensity at the surface of the Earth at this point so that the VE becomes equal to square root of 2E R, because we know that J is also equal to E. So this is another relation that can also be used to find escape velocity. Another relation can also be used to find the escape velocity. So take note of these equations and you can be asked to prove it or use it in any calculation at any point in time. Good. Another important velocity that we need to look at is critical velocity. Now, critical velocity is the velocity with which a satellite moves horizontally when it is launched into space onto its orbit. You know, when the satellite gets to its orbit, the satellite then assumes horizontal position, then it begins to move around the Earth. The velocity with which the satellite moves around the Earth horizontally is what we refer to as critical velocity. So let's obtain an expression for this critical velocity. Good. So critical velocity. To do this, you know the satellite is going to move on a circular orbit, so it will have centripetal force. To have centripetal force, Fc is equal to mv squared over r. Let's call this equation 1. But the centripetal force is made possible by gravitational force. Gravitational force between the satellite and the Earth. So that gravitational force, F is equal to G, capital M mass of the Earth, small m mass of the satellite, divided by r squared. So in order for the satellite not to escape, the centripetal force must be equal to the gravitational force, F. So we say mv squared over r is equal to G, capital M, small m over r squared. So this m will cancel this m, and this r will cancel one of these r's. So I'm going to get v squared is equal to G, capital M over r. G, capital M over r. Then we make v the subject. That gives us v is equal to square root of J capital M over R. This is the critical velocity, the velocity with which a satellite moves horizontally around the Earth. Take note of this. The escape velocity VE is given by square root of 2Jm over R. Don't be confused with these two. This formula is for the escape velocity. It has 2 here. This formula is the critical velocity. So what that means is that square root of twice the velocity of the critical velocity is equal to the escape velocity. Take note of that. Now, these two velocities have relations that are very important and we need to take note of. Remember, the satellite shall revolve around the Earth in elliptical orbit when V is less than VE. Alright, I hope you can see. When the critical velocity is less than the escape velocity, then the satellite will undergo elliptical orbit around the sun. Around the planet. The satellite will undergo elliptical orbit around the planet. When V is equal to VE, that is when the critical velocity is equal to the escape velocity. It's equal to the escape velocity. The satellite will move on a parabolic orbit. In the first instance, the first case, when the critical velocity is less than the escape velocity, then the satellite will move on an elliptical orbit around the sun. This is the satellite. This is the satellite. This is the Earth or the planet. So the satellite will move on an elliptical orbit around the planet. Good. But when V is equal to E, that is VE, when the critical velocity is equal to the escape velocity, then the satellite will move on a parabolic orbit around. The satellite will move on a parabolic orbit like this. To move on a parabolic orbit. What that means is that the satellite will move up into space and fall back onto the Earth's surface. To move parabolic orbit, to fall back onto the Earth's surface. It will not be able to revolve around the sun, around the Earth. Then 3. When V is greater than VE, that is when V is greater than VE, that is the critical velocity is greater than the escape velocity, then the satellite will move in a hyperbolic orbit. The satellite will move in a hyperbolic orbit. This is the satellite. The satellite will move in a hyperbolic orbit like this. Alright, you see, in the parabolic orbit, there seems to have a certain horizontal distance. In the parabolic orbit, the tip here has a peak. Exactly. So, when in the third scenario, when the critical velocity is greater than the escape velocity, then the satellite will move in a hyperbolic orbit. Will move in a hyperbolic orbit. And the last one, when the critical velocity V is equal to square root of GR, where R is the radius of the Earth, then the satellite revolves in a circular orbit around the Earth. The satellite revolves in a circular orbit around the Earth. Circular orbit around the Earth, like this. So when the condition is like this, the critical velocity is equal to G, which is the acceleration due to gravity times the radius of the Earth, times the radius of the Earth, then the satellite moves on a circular orbit. When V is greater than VE, the satellite moves on a hyperbolic orbit. When V is equal to VE, then the satellite moves on a parabolic orbit. Then the satellite revolves around the Earth on an elliptical orbit when V is less than VE. I'm supposed to prove for the period of a satellite, as it revolves around the planet. I'm supposed to prove the period of a satellite for you, but I will do that later in this same video. I will do that. Just that it has some links with Kepler's Kepler's third law of planetary motion. So when I do the Kepler's third law of planetary motion, then I'll bring that aspect in so that it can save us time and data. All right, good. So let me touch on the uses of satellites. Uses of satellite. The satellites are used for communication purposes. When I say communication purposes, it cuts across a whole lot of field. For instance, satellites are used to transmit television signals. Satellites are used to transmit, audio visuals. They are used to transmit telephone signals from one place to another. That is the reason why we can have ground-based satellite and then a space-based satellite. A ground-based satellite is a satellite which is positioned somewhere on the Earth's surface, and then as the Earth rotates, the satellite also moves alongside. And a space-based satellite is a satellite which is positioned somewhere in the atmosphere, somewhere in the sky, so that it can pick information from the Earth's surface or from the sky and send it to the Earth's surface. So that is ground-based satellite and then space-based satellite. Now let me share some small light on that. Ground-based satellites, because they are positioned somewhere on the Earth's surface, cover a small area. But space-based satellites cover a very large area. So it is a space-based satellite has an advantage over a ground-based satellite in that a space-based satellite is able to cover a very large area. Just one satellite will cover a very large area. But a ground-based satellite will cover a small area. So to cover the same area as a space-based satellite, you need to erect a number of satellites. This is the type of satellite that companies like MTN, Vodafone, and then they use in Ghana. Good. They use ground-based satellites. Then, but the advantage that the ground-based satellite has over the space-based satellite is that it is cheaper. It is cheaper to manage a ground-based satellite than to manage a space-based satellite. All right. That is the advantage of a ground-based satellite over a space-based satellite. So let's go back to the uses. We say it is used in communication purposes like television transmission and then telephone transmissions. It is used for navigation. It is used for weather forecasting. It is used for remote sensing, and then it is also used for aerial photography. Let's look at the Keplers laws of planetary motion. Like I always say, if you haven't subscribed to my YouTube channel, which is BJ Online, please subscribe to the channel, and when you do that, turn on the notification so that anytime a video is uploaded, you will get a notification and then you watch it. Thank you. Now let's look at Kepler's laws of planetary motion. Kepler was an English scientist. He is one of the renowned scientists that the world has ever had. Now, he came up with 3 laws that govern the planetary motion. So the first law, Kepler's first law is also called the law of So Kepler's first law is also called the law of orbit. And this law states that every planet revolves around the sun with the sun at one focus. What this means is that all the planets undergo circular motion around the sun and the sun is stationary at one point. That is Kepler's first law. that all the planets revolve around the sun with the sun at one focus. Then we look at the Keplers second law. The Keplers second law is also called the law of area. The law of area. And this law states that a straight line that joins a planet to the sun sweeps equal areas in equal time. Let me illustrate this with a diagram. This particular law has a lot of meaning. Good. So, let's look at this. For instance, let this be the Earth. Sorry, let this be the orbit of the Earth. And let this be the sun. So this is the sun. And this is the Earth. So the Earth is moving around the sun. What Kepler is saying is that a straight line that joins a planet to the sun sweeps equal areas equal times. Good. Now because the planets move on elliptical orbits, at one point the planet is closer to the sun, and at one point the planet is far away from the sun. So when the planet is closer to the sun, let's say the planet moves from this point to this point. Now, in order to cover the same area, alright? In order to cover the same area, let me shade this part like this. And then let me shade this part like this. What Kepler is saying is that a straight line that joins a planet to the sun sweep equal areas A1, A2 in equal times, T1 and T2. What he's saying is that if A1 is equal to A2, then T1 is also equal to T2. So let's look at this. At this point, the planet is closer to the sun. At this point, the planet is far away from the sun. So if this area is equal to this area, then this time is also equal to this time. What is the meaning of this? The meaning of this law is that, when you look at this critically, the distance from here to here is smaller than the distance from here to here. So if the distance from here to here is smaller, and the distance from here to here is large, then why then the time here from here to here is equal to the time from here to here? This can only happen when at this point the planet moves faster. And at this point, the planet moves slowly. Then at this point, the planet moves faster. Let me explain that again. How can the distance from here to here be shorter than the distance from here to here, yet the time taken to travel from here to here be equal to the time taken to travel from here to here? This can only happen when the planet moves from here to here faster than it moves from here to here. What this means is that when the planet is far away from the sun, it moves slowly. But when the planet is closer to the sun, it moves faster. That is the interpretation of the Kepler's second law of motion. Kepler's second law of planetary motion. When the planet is closer to the sun, it moves faster. But when the planet is far away from the sun, it moves slowly. Then we look at the Keplers Third Law. Take note of this Keplers Third Law very well, because you may be asked to prove this law, and White has asked it several times. So Keplers Third Law of planetary motion, it states that the square of the period of revolution of a satellite, the square of the period of revolution of a planet is proportional to the cube of the distance between the planet and the sun. Let me take it again. The Kepler's third law states that the square of the period of revolution of a planet around the sun is proportional to the cube of the distance between the planet and the sun. Let me illustrate this. Good. So we say let this be the sun, and this be the orbit of a planet. Let the planet be Earth. So this is the Earth, and this is the sun. Let the distance from the sun to the Earth be r. What the law states is that t squared is proportional to r cubed, where t is the period of revolution of the planet around the sun. R is the distance from the center of the sun to the center of the planet. Good. You can be asked, or you may be asked to prove this particular relation. So I'm going to prove this relation, and after I have proven it, we use the same relation to also determine the period of a satellite. Good. So let's do this. We want to show that t squared is proportional to r cubed. We want to prove this relation, which we call the Keplers Third Law. So to do this, let me make a rough sketch of what I'm going to do so that you can picture it. Let r be the distance from here to here. Let m be the mass of the sun. Let small m be the mass of the planet. Let t be the period of the planet. Remember that the planet is undergoing circular motion, so the planet has centripetal force. So the centripetal force Fc is given by m omega squared r. This is another relation for centripetal force. And because I want the period, that's why I quoted this relation. Good. Let me call this equation 1. And the circular motion is made possible by the gravitational force. Between the sun and the planet. So that gravitational force is given by F is equal to m omega squared. G capital M small m over r squared. Let me call this equation 2. So in order for scaling not to occur, the two forces must be equal. The Fc must be equal to the F. For that matter, I can write m omega squared r is equal to G capital M small m over r cubed over r squared. Good. So I make this m, we'll cancel this m, and then this r will multiply by this r. When I divide here by r, I divide here by r, the r will multiply this. So that is going to give me omega squared is equal to G capital M over r cubed. G capital M over r cubed. Good. But omega is angular velocity. And angular velocity is given by 2 pi over t. We saw this from circular motion. So when we put this here, that is going to give us 4 pi squared over t squared is equal to J capital M over r cubed. See that the t squared is coming and the r cubed is also coming. So when I divide through both sides of the equation by 1, I will get t squared over 4 pi squared is equal to r cubed over J capital M. And I'll make t squared a subject. T squared is equal to 4 pi r cubed all over Gm. Look at this. 4 is a constant, pi is a constant, G, universal gravitational constant, and m, the mass of the earth, is constant. So you realize that the whole of this is a constant. So we say let k represent 4 pi squared over Gm. Let k be equal to 4 pi squared over Gm. So in place of the whole of this, I put k to get t squared is equal to k r cube. So when I remove the proportionality constant, I introduce a proportionality sign. T squared is proportional to r cube. This is the proof of the Keplers third law of planetary motion. All that you need to go through this proof is the centripetal force relation, the gravitational force relation. You equate the two of them, then you simplify, you make t squared the subject. Good. You remember, I have already spoken about the formula for finding the period of a satellite. If you want to find the formula for finding the period of a satellite, you go through the same process. The formula for finding the period of a satellite. Then when you get to this point, at this point, you don't come this far. You make t the subject here to give you t squared, t is equal to square root of 4 pi squared r cube all over Gm. So this will give us t is equal to 2, square root of 4 is 2, square root of pi squared is pi, then square root of r cube over Gm. This becomes the formula for finding the period of a satellite. It was for the sake of time that I did not go through the proof, then I'll go through this one. So if you want to find the formula for the period of a satellite, all that you do is that make t the subject in this equation, and then you get this. But if you want to prove the Keplers third law, then when you get here, you proceed in this direction, and then we'll finally arrive at this. Good. So this brings us to the end of gravitation, but I will try as much as possible and do another video on how to solve some few questions on this topic. When you meet some questions and you're unable to solve, you post them to me on the Facebook page, then I will solve it. The Facebook page is PJ's Physics Classroom. Then I'll solve the questions and then I'll send it to you so that you watch it. Thank you very much for being part of the show. It's your man BJ. Take care of yourself.